morning to all. In this video, in this gate video, we're going to see about small signal model BJT, small signal model bipolar junction transistor, and it was going to be presented by me, Dr.V.Premchandran, ME PhD, MASTE, Assistant Professor, Department of ECE, Erode, Sengunthar, Engineering College, Erode, Tamil Nadu. So, what do you mean by BJT? BJT is nothing but bipolar junction transistor. Bipolar junction transistor. So, what is the transistor? Bipolar. The term bipolar, what does it mean? The current connection in this device is going to be happen due to both the charge carriers. One is electron and other one is holes. So, in this device, the current connection is going to be taking place by both the charge carriers. That's why it's termed as a bipolar. And then junction, it has more than one junction. So that's why the junction term has been used in the title. And transistor. What do you mean by transistor? Transistor means it's nothing but transistor is commonly called as a transistor. So what does it do in this? By making arrangements, you can transfer the resistance property of the one side of the device to other side of the device. That's why it's called as a transresistance. The resistance property is keep on varying based on the power supply and current conduction and current flowing in the device. That's why it's called as a transistor. Right. Now we shall get into the topic. Introduction to the amplifier. Amplifier. So what do you mean by amplifier? A device or circuit which is used to increase the strength of the signal, whereas the input signal has the less strength and output signal has the highest strength. So what has happened? We are just boosting the strength of the signals. So the boosting of the signal is termed as an amplification. So the device which does do this operation is called as an amplifier. So in electronics, this amplification process can be done with the help of the amplifier, and that amplifier, the basic device is not just nothing but the device which does do the amplification is nothing but a transistor. So mostly BJT is have been seen wherever the amplification process is taken. There the BJT has been seen. I think you're able to understand. Right. Fine. BJT, amplifier, transistor, bias. Fine. Okay. So what are things we're going to see in these slides? Means amplifier, a transistor biased in the black part of the IV curve. BJT forward active region, Mosfet saturation region. In these regions, transistor can provide high voltage current type power gain. Bias is provided to stabilize the operating point. Viewpoint. Viewpoint is nothing but balancing point in the desired region of operation. Viewpoint also determines small signal parameter of transistor, voltage gain, input resistance and output resistance, maximum input and output signal amplitude, and power consumption. So what do you mean by viewpoint? Based upon the power supply given to the amplifier circuit, we can vary the operating point. There's nothing which is called as a viewpoint. I think you're able to follow me. Right. So meanwhile, we can see about the amplifier using BJT. Right. There are three basic BJT amplifier configurations that are generally identified as a common emitter, common base, and common collector. Sometimes called as an emitter follower. Common collector is also called as an emitter follower. Each of these configurations exhibits certain characteristics that makes them more desirable in certain current circuit application. Right. BJT common amplifier. In this circuit, uh, before that we shall have a look on some of the things. Okay, active region. The transistor's ability to change between these two states. This have two functions, switching and amplification. Then bipolar transistors have the ability to operate with the uh, with the three different regions. Active region, the transistor operates as an amplifier, and saturation region, the transistor is full on, operating as a switch. IC is equal to I saturation. IC is equal to beta IB is amplification active region. Well, as the bipolar transistor is a three-terminal device, there are basically three possible ways to connect it within an electronic circuit, with one terminal being common to both input and output signal. Each method of connection responding differently to it. Input signal within a circuit and static characteristics of the transistor vary with each circuit arrangement. Common base configuration has voltage gain but no current gain. Common emitter configuration has both current and voltage gain. Common current gain configuration has current gain but no voltage gain. Hmm. In common collector or a ground collector configuration, the collector is connected to the ground to the supply. This collector terminal is common to both the input and output. The input signal is connected directly to the base terminal, while the output signal is taken from the across the emitter load resistance as shown. This type of configuration is known as voltage follower or emitter follower circuit. The common collector or emitter follower configuration is very useful for impedance match application because of its very high input impedance in the region of hundreds of thousands of ohms while having a relatively low output impedance. The it's very useful for impedance matching application because of its very high input impedance in the region of hundreds of thousands of ohms while relatively high configuration. Right. In common emitter or grounded emitter configuration, the input signal is applied between the base emitter while the output is taken from between the collector and emitter as shown. This type of configuration This type of configuration is the most commonly used circuit for the transistor-based amplifier and which represents the normal method of bipolar transistor connection. The common emitter amplifier configuration produces a high current and power gain. Of all three bipolar transistor configurations, this is mainly because the input impedance is low and it is connected to the power bias PN junction, while output is high impedance as it is taken from the reverse biased PN junction. As its name suggests, in common base, as the ground base configuration, the base connection is common to both input and output signal. The input signal is applied between the transistor's base and the emitter terminal, while the corresponding output signal is taken from between the base and collector terminal as so. The base terminal is grounded or can be connected to some fixed reference voltage point. The input current flowing into the emitter is quite large, as it is sum of both the base current and collector current respectively. Therefore, collector current operates and collector current output is less than emitter current input resistance. In a correct case for this type of circuit, one or unity, or let's simplest word, common base notation, attenuates the input signal. Right. I think we have been sufficiently known about these things. Right. Characteristics. You can see the characteristics of common base, common neutral, and output. Regarding the input impedance, common base has low input impedance, common neutral is medium, and common collector is high. Output impedance. Common base is very high, common emitter is high, and common collector is low. Phase shift. Uh, Other than common emitter, all are zero phase shift, whereas common emitter is 180 degree phase shift. Voltage gain. Common base has high voltage gain, common emitter is medium, and common collector is low. Current gain. Common base has a low, common emitter is a medium, common collector is a high. Power gain. Common base is low, common emitter is very high, whereas common collector is a medium. So we have been seeing the sufficient amount of the characteristics of the devices. Right. Now, what is meant by Q point? Next, we have seen about the Q point. Q point. It's a very important thing. Fine. Transistor device which act as an amplifier. The amount of amplification is measured in terms of gain. For transistor to act as an amplifier, the gain has to be constant. If it is not so, it is meaningless to have amplification. Everyone wants faithful amplification so that they can use it in speaker, carrier wave, or for signal transmission, etc. Amplification is done by superimposing the input base current on DC voltage current. But sadly, transistor cannot superimpose the input AC a signal on all DC connector. For a constant for a constant input base current, the current connector should be constant, but it is not so on some region of curve. These rows in those regions, transistor either completely conducts or it can completely stops conducting, which is not suitable for amplification. Hence, collector voltage should be selected carefully. The point on the output characteristics curve is called Q point, operating point for listening point. Q is the constant DC voltage or current given to the collector terminal for its operation. When transistor acts as an amplifier, this point has to be maintained constant. That were that were biasing helpers to providing the constant DC voltage to get the Q point. Let's get into the topic. Let's get into the okay. Let's see this. To get the Q point lies on the load line. Sorry, before that, when transistor acts as an amplifier, this point has to be maintained constant. That BIS helps to providing constant DC voltage. To get the Q point lies on load line. Load line in the load line is the line joining the points maximum output at zero collector voltage and the maximum output voltage at zero collector current. DC loading is also obtained by DC analysis of transistor. Generally, the midpoint of this line considered as a Q point for amplification, so that it can amplify upper and lower parts of the input signal. We can see that in those regions, output collector current is constant for unchanged input base current. In cases like when no input signal is given, voltage at the collector Q point voltage is received as the output signal. If Q point is near the saturation region, current rises rapidly or cutoff region. Or cutoff region. Current rises rapidly and not cutoff region. Current flow is very low. The transistor act as an on and off switch respectively. So in general, Q point which determines the actual operation of the transistor and that by even transistor is represented in Q1, Q2, Q3. Fine. Here you can see the transistor BJT amplifier concept. So here BJT transistor is nothing but a NPN transistor. So here it has been given as a bias and then through the base input is given to the circuit. So the BJT is biased in active region by DC voltage. The example we want to set as a IC set as IC by VC is equal to 1 by NA 5 volt with the IB is equal to 15 microamps. B is equal to 100. So total base emitter voltage is VBE is equal to VBE plus VBE. And whereas both the VBE, both the VBE, what does it say? It's nothing but one is, uh, whereas one is DC current and other one is AC current. Right? Battery voltage ECE is equal to VC, whereas ICRC. This is the load line equation, and then it's going to be seen in the next slide. BJT amplifier as continued. So you can see the Q point over here. So in this diagram, we can see many other things. Right. Draw this diagram and take down this thing. Right. Transistor amplifier, BJT amplifier. In transistors, there are two types. One is BJT, another is JFET. In that we go to the BJT has the uh, high switching characteristics. Sorry, it has low switching characteristics, but has amplification property is very high. Right. So here you can see uh, the DC load line and AC input signal. You can see the lines which have been the voltages which has been converted from 0 to 12 in which has been easily segregated as 2, 4, 6, 8, 10. Plus current is going to be transfer is 2.0 milliamps. Just each is considered as a step 1, 2, 3 MA. So by adjusting the DC supply, by adjusting the bias, we can change the Q point. If the Q point is in the middle of the region, then we can see the high voltage gain and high current gain. Right. You can see 8 millivolts peak voltage changes in VBE given as 5 MA. Change in IB at 0.5 MA. Change in IC 0.5 milliamps. Change in IC produces a 1.6 voltages. Change in VC. If changes in operating current and voltage enough, then the DC, then the IC and VC waveform around as undisorted triplicates and up triplicates of the input signal. A small voltage change at the base cause a large voltage changes at the cutter. Voltage gain is given by AB. The voltage gain is noted as AB is equal to VC by VBE 1.65. If the magnitude and its degree is 180 degree. And VB, if the VBE strength is 0.008 and 0 degree, which is equal to 167, 180, 206. Minus indicates the volatility phase shift between the input and outputs. VBE gives 5 milliamps changes in IB, right? 0.5 MA changes in IC, and 0.5 MA changes in IC produces 1.6 changes in VC. If changes in operating current and voltages are small enough, then AC and DC waveforms are undistorted duplicates of the input signals, while IC is the AC current and VCE is the AC supply. A small voltage changes at the base causes a large voltage gain. At the altar, voltage gain is given by AV, VCE is equal to VB and 1.65 is the magnitude and 1 degree is the angle of the voltage. Cut emitter voltage. What is the base emitter voltage is nothing but 0.008 and degree indicates as a 0. So totally what is the voltage gain? Voltage gain is 0.6 and angle is 180 degree phase shift and this is about minus 206. So here this circuit is a MOSFET amplifier concept. So what is MOSFET? Let's see about the MOSFET and then we should get into these kind of questions, right? Okay. MOSFET is a type of a it's a type of a field of a transistor. So MOSFET is a term that's a metal oxide semiconductor. Metal oxide semiconductor. It's a metal oxide semiconductor field of a transistor. This term is a MOSFET, also known as a metal oxide silicon transistor, is a type of insulated field of a transistor that is fabricated by controlled oxidation of semiconductor, typically silicon. The voltage of the converter gate determines the electrical conductivity of the device. This ability to change conductivity of the amount of applied voltage can be used for the amplification or switching electronic signals. The MOSFET was invented by Mohammed Atalia and John Kang at the Bell's Lab in 1959. They first present in 1960. It is the basic building block of the modern electronics and most frequently manufactured devices. In history, with estimated total of 13.66 trillion, most was manufactured between 1962 and 18. It is the dominant semiconductor device in digital analog integrated circuit, the most common power device. It is a compact transistor that has been miniaturized and mass-produced for a wide range of applications, revolutionizing the electronic industry and the world economy, and be central to the digital revolution, silicon age, and information age. Most but scaling and miniaturization has been driving the rapid exponential growth of the electronic semiconductor technology since the 1960s. It enables high-density ICs such as memory chips microprocessor. The Mosfet is considered as the workhorse of the electronic industry. The key advantage of the Mosfet is it requires almost no input current to control the load current when compared to the bipolar junction transistor. In enhanced mode, Mosfet voltage applied to the gate terminal can increase the conductivity from normal off state. In depletion mode, the voltage applied to the gate reduces the conductivity of the normal on state. Mosfets are capable of high scalability, with increasing the miniaturization can be easily scaled down to the smaller dimension. Crystal scale. Mosfet can be either manufactured by the part also cheaper, lesser, and also high density compared to the BJT. The key advantage of the MOSFET is it requires almost no current to the control the load current when compared to the bipolar transistor. Enhancement mode. Voltage applied to the gate terminal can reduce the conductivity from normal off state in the depletion Voltage gain applied to the gate can reduce conductivity from the normal off. MOSFET can also capable of high scalability with increasing miniaturization, easily scaled up to the smaller dimension. MOSFET can either manufacture as a MOS integrated circuit chips, as a discrete MOSFET device, such as power MOSFET, and can take the from signal gate or the SIM and multi-gate transistor. Since MOSFET can be made with either P-type or N-type semiconductor, PMOS or NMOS logic respectively complementary pair MOSFET can be used for making switching circuits with a low power consumption CMOS logics. A metal oxide semiconductor typically refers to the metal oxide oxidation insulation semiconductor. Typically, however, the metal is a MOSFET. It's a misnomer because gate materials can also be layer of polysilicon along with oxide and different electronics materials and connect the smaller high voltage and most capacitors also MOSFET structures. And it has a huge concept behind it, right? Operation. The traditional metal structure is obtained by growing the silicon dioxide not as much of the thing which get how it has been seen, how it has been used, and the purpose of the amplification. MOSFET amplifier. In other words, we can control how the MOSFET. Here we're going to see how the MOSFET is used in the amplification process. In other words, we can control how the MOSFET operates by creating enhancing connectivity channel between the source and drain regions, providing a type of MOSFET commonly called as a N-channel enhancement mode and MOSFET, which simply means that unless we bias them positively with gate negatively up for P-channel and no-channel current will flow. There are large variations in the characteristics of different types of MOSFET, and hence the biasing of the MOSFET uh, must be done individually, as within the bipolar transistor common emitter configuration. The common source most MOSFET amplifier needs to be biased at the suitable constant value. But first, let's the remains also the MOSFET basics. Enhancement MOSFET or MOSFET classified as a normally of devices that only connects when the suitable gate to source voltage is applied, unlike depletion MOSFET, which are normally on devices connecting when the gate voltage is zero. However, due to the construction of the physics enhancement type of MOSFET, there is a minimum to the gate source voltage called threshold voltage. That is, there must be a gate before it to be start connecting, allowing the drain current to flow. In other words, enhancement MOSFET not connect when the gate source voltage, which is less than the threshold voltage VTH, but the gate forward bias increases. The drain current ID, also known as the drain source current IDS, will also increase similar to the bipolar transistor, making e-MOSFET ideal for use in MOSFET amplifier circuits. The characteristics of MOSFET conductive channel can be under a variable resistance that is controlled by the gate. The amount of drain current flows this N-channel therefore depends on the gate source voltage and not the many measurement we can take using MOSFET is to transfer characteristics to the stores the IV relationship between drain current and the gate source voltage. Also, N-channel E-MOSFET the IV characteristics. The fixed bias VT current drain source voltage corrected across E-MOSFET can plot the values of the drain current IT with the varying values of VGS to obtain the correct MOSFET power biased DC characteristics. The characteristics are given by the transconductance Cm of the transistor. The transconductance relates the output current to the fixed Input voltage can represent the gain current in a transistor. The slope of the transconductance curve at the ATV point given therefore given as a Gm is equal to IDV VGS at the constant value of ADS. So for example, Mosfet transistor passes the drain current of the 2 milliamps 2 milliamps when VGS is equal to 3 volt and drain current is equal to 40 milliamps when VGS is equal to 1 volt. Then Gm is equal to IT by VGS, which is nothing but 14 minus 2 into 10 to the power minus 3 by 7 minus 3, which is 3 minus 3 ms. This ratio is called as a transistor static or DC conductance, which is stored for the transconductors as given by the unit of the Siemens, as it is the ampere per volt voltage gain. The most important way is static with the transconductance and its value drive resistance. So, in this MOSFET amplifier, we are giving the input at the point of the gate, this is the supply, and at the point of the the source, we are getting like the output here. The Q point from the curve, which is understand. The Q point is being maintained at the center of the sink. So by this, I can get more number of amplification. The amplification, voltage amplification, it has been seen. The value is -4, whereas high amplification is done. The minus sign indicates it is in phase shift operation. Most of this biased active region for the voltage gain source VGS. Example, Q point is set at the ID common VTS is equal to 1.56 milliamps, 4.2 volt, and with the VGS is equal to 3.5 volt. Total gate source voltage is VGS is equal to VGS plus VGS. One VP changes in the VGS is 1.25 milliamps, 82 changes in ID, and 4 VP changes in the VGS. Are able to follow me? Okay. So what the other things I've been going to see? That's going to see to how it has been going to work it to right. The MOSFET is biased to the active region by DC voltage. So active region is maintained by using the DC voltage applied to the MOSFET, VGS example Q point set at the IT now VGS is equal to 1.5 milliamp, 1.6 milliamps at 4.8 volt. With the VGS is equal to 3.5 volt. Total gate source voltage is given as VGS is equal to VGS plus VGS. 1.2 point voltage changes in VGS is 1.2 milliamps. Hence the idea and the VP means. Yeah. In this slide, we're going to see the transistor wave coupling and bypass capacitor. AC coupling region will the capacitor. So in this, so here we're going to see the transistor coupling and bypass capacitors. What is a capacitor role in the transistor? Capacitors or the capacitor. Okay, AC coupling with capacitors is used to inject the AC input signal and external output signal without disturbing the Q point. So whatever the AC current given to the application, it may changes the biasing setup. To avoid those biasing setup, we are going to use this coupling capacitor. If the biasing setup has been changed, what has happened? The Q point will be varying, whereas we are used to maintain the constant output. So that so for this reason, what shall we do? Here we're going to add a capacitor in the given input region and output region. By that, the AC supply application models will does not affect the fixed does not affect the bias setup, right? Coupling to the capacitor is used to inject the AC input signal and X output signal without disturbing the Q point. Capacitor are designed to provide a negligible impedance at the frequency of interest, provide open circuit for a DC, C1, C2, or low impedance. Coupling capacitor or DC blocking capacitor. whose reactance at the signal frequency is designed to be negligible. C3 is the bypass capacitor that provides a low impedance path for AC current from emitter to ground, thereby removing or evacuate good resistability from the circuit as the AC signal to be considered. Right. Whenever the AC signal passes the emitter, it should not choose the path of R1, it should chooses the path of C1. Whereas R1, the purpose of the R1 is in biasing. Right. That's why we are using this bypass capacitor to pass us over the AC current without creating the resistor. By that I can maintain the Q point constant. Transistor amplifier DC and AC analysis, two-step analysis. DC analysis find the DC equivalent circuit by replacing all capacitor by open the circuit and inductor by short circuit. Find the Q point from the DC equivalent circuit by using appropriate logic and transistor. AC analysis. Find the AC equivalent circuit by replacing all capacitor by short circuit. Inductor by open circuit DC voltage source by the ground connection and the DC current source by open circuit. Replace transistor by small signal model. Use a small signal AC equivalent circuit to analyze the AC combined and the result of the DC and DC analysis to give voltage gain and current to the network. DC analysis. Finding the DC equivalent circuit by replacing all capacitor. Open circuit inductor by short circuit. Find the Q point for the DC equivalent circuit by using appropriate non-signal transistor model. AC analysis. Find the AC equivalent circuit by replacing all capacitor by short circuit. Inductance. By open circuit DC voltage source by the ground connection DC current source by open circuit. Replace the transistor by small signal model using a small signal AC equivalent circuit to analyze the AC capacitor and amplifier. Combine results of the AC to get good voltage network. So you can see the diagrams of the AC equals circuit. Just to take on the diagram, I'll type diagram. By copying this, we can make it understand it very clearly. So in these circuits, we can see three different circuits. And the very first circuit, left common circuit it's a transistor circuit in which it has been passing, but it has in all the connections. It has AC/DC connections. Whereas here we're going to segregate into two types: capacitor replaced by short circuits, and instead of capacitor devices that we can use as circuit since other two circuits deals with only the AC. For the AC supply, what does that means? For the AC supply, it has been seen as a short circuit, and that's why the capacitor has been not replaced in the AC equivalent circuits. So here, all the resistors has been by using some properties. We have been making as a single. All the three resistor has been converted as a single resistor, the two resistors, and it has been replaced by the parallel resistance concept as a single resistance. This is what this maximal operation of BJT amplifier. So, in the previous slide, what we have seen has been converted in some other form. Small signal. This is for analysis purpose. We are representing the signal, the transistors in this case, and by this we can make the proper analysis. This is the important thing. Okay, for the small signal, how the transistor is going to react, that can show, and its background, how it has been functioning over the signal has been shown in this diagram. The hybrid pi small signal model is the intrinsic representation of BJT. Small signal parameters are controlled by the Q point or independent of the geometry of the BJT, which is not about the size of the BJT. Transmitted is G is equal to IC minus VT, which is equal to 40 IC. And input resistance pi is equal to beta of VT by IC, which is equal to beta of GM or beta of GM R pi output resistance. So VA plus VC is equal to IC is equal to VA by IC. The common emitter with small signal. Okay, here in this we're going to see how the common emitter is used in the amplification process and its small signal analysis. So you can see the common emitter configuration. BC cells are 12 volt, and R2 is the 1300 kilovolt, and R1 is the 16 kilovolt in the circuit first circuit left hand side, whereas C1 is the values being it's equated to the infinity, whereas its value is very low, it's normal one. But due to the property for AC, DC supply tag as an infinity, that's what we indicate as an infinity, whereas R3 is equal to 100 kilovolts, and whereas RC is equal to 22 kilovolts, and RE is equal to 13 kilo ohms. So here you can see the AC equivalent circuit in the right side of the thing, right side of the slide. Like left side you can see about the DC equivalent circuit. And AC equivalent circuit is constructed by assuming that all capacitance are zero impedance at high frequency, the signal frequency, and the DC voltage shows as a AC current, assuming the Q point is already known. So these things I can see in this slide. And next slide, we're going to see the common emitter amplifier, a small signal equivalent circuit. So for the common emitter circuit, amplifier circuit, we're going to see the small signal equivalent circuit. So here, in this in this thing, you can see this the resistance, the heavy resistance R1, RB, and VB, and we can see about the J and VB itself, which is nothing but the resistor current gain and the R2 of the R6 with R3. all these we're going to see it over here. Right. And in the nearby circuit, all the resistance R1 or RB has been R1 RB has also been seen. And instead of the R naught or RC, it has been replaced by the RL, or the low resistance. Whenever the resistance the output has been load has been always indicated as a resistance for the purpose of the analysis. Input voltage is applied to the base terminal and output signals are appears in the correct terminal. Emitter is the common to the both input and output signal. Thus, circuit is termed as a common emitter amplifier. The terminal gain of C amplifier is the gain from the base terminal to the collector terminal. ACE by VT is equal to VC by VB. GM order. Just would always study, but the R naught is parallel connected with the RC and just parallel connected with the R3. So all the parallel connector resistance has been replaced by the RL. RL is the load resistance, but AVT is the voltage gain of the C configuration. And the voltage gain deals with the output voltage by input voltage, whereas GM is the transconductance, whereas the output, whereas RL is the output power driving thing. So here we can see the common amplifier input resistance. So input resistance also plays the important role in the amplification process and the signal source gain. So here analyzing the input resistance is also a very important parameter. So you can see defining RAB as input resistance, looking into the base transistor. RAB is equal to VB by this input resistance, which depends upon the input voltage value and input current value. VB by IB is equal to R pi. The input resistance presented to the VA is equal to RIN, which is equal to R1 plus RB is parallel to the RAB, therefore R1 plus RB parallel R pi. So this is the input represented to VA. Thus the signal source voltage gain is equal to AV, C is equal to V naught by VB, which is equal to V naught by VB by VB by VB, V naught by VI, output voltage by input voltage. So, but for proper analysis purpose, I'm including the two factors called the VB, which I going to multiply the both the upper side and downside side. And finally, AVT is equal to the, it's a between the resistance, it's a parallel resistance between the RB and R5 and R1 and RB, it's a parallel resistance. You can see how it works, right? Common amplifier voltage with example. Yeah, here we do the real-time example. Here we're going to analyze the value. So here in this problem, we're going to calculate the voltage gain and input resistance and maximum input signal level for the common emitter amplifier. In this circuit, we can see all the things has been declared in its value. As always 1 kilo ohms and R2 is 300 kilo ohms and RC is 22 kilo ohms and base is 12 volt, whereas R1 is 160 kilo ohms and since C1's value is high, so we represent as infinity. And RC, the capacitance, compared to capacitance is 22 kilo ohms, and RE, emitter resistance is 13 kilo ohms, and C2 is the coupling capacitor, and R3 is the load or the output we are going to taken over. This is equal to 100 kilo ohms, right? So calculate the voltage gain. So in this problem, I'm going to calculate the voltage gain, input resistance, and maximum input signal level for the common emitter amplifier given data. Okay. From the problem, from the circuit diagram, we are taking the many facts. In that beta factor is equal to 100 and VA is equal to 75. Q point is at the point of 0.245 milliamps and 3.38 volt assumption. So by our problems, there should be I have some assumptions. So that way the transistor is an active region and beta naught is equal to beta F. Signals are low enough to be considered a small signal room temperature analysis. GM is equal to 40, IC is equal to 40, 0.245 milliamps is equal to 9.80 milliseconds. So GM is equal to millisieverns. So first I want to calculate the transconductance. The transconductance value is equal to 40 into IC, whereas the IC is equal to formula where IC is the Z is equal to 2.45 milliamps, which is equal to 9 as Siemens. Alright, I should calculate the input. I should calculate the input resistance. Alpha is equal to beta by GM, and 100 by 9.9 ms is equal to 10.2 kilo ohms. So this is what the input resistance of the circuit providing. And next, I'm going to calculate the output resistance. Output resistance is simple. I'm going to calculate the output voltage by the output current. By that, I'm going to calculate together. I'm going to get the value of the output resistance, which is equal to software, whereas input voltages are equal to VA by VCE 70 volt plus 3.39 volt divided by 0.245 milliamp, which is equal to 320 kilo ohms. Right? Whereas RB is equal to R1 parallel to the R2, which is equal to 160 kilo ohms parallel to 300 kilo ohms, which is equal to 104 kilo ohms. And R is equal to R0 parallel to the RC parallel to the RL, which is equal to 320 kilo ohms parallel to the 22 kilo ohms, which is parallel to the 100 kilo ohms, which is equal to 17.1 kilo ohms. RB parallel to the R base is equal to 10, 104 kilo ohms parallel to the 10.2 kilo ohms, which is equal to 9.25 kilo ohms. So the problem is keep on continuing. So I want to the problems keep on continuing. So in this, I will be going to affect the voltage gain. So I just have to put the minus Gm by order is equal to R be parallel to the R prime. And R is plus R of is parallel to the R prime, which is equal to 9 millisieverns into 17.1 kilo ohms into 9.29 kilo ohms divided by 1 kilo ohms plus 9.29 kilo ohms. Finally, the value has been gain has been found out, which is nothing but minus 168.093, which is nothing but minus 151. So the gain is 151. The minus indicates the phase shift of the signal. And what is the input resistance? Input resistance R1 plus RB, which is parallel to the R5, which is equal to 10.3 kilo ohms. This is the input resistance provided by the circuit. Next, VBE, separate the base emitter voltage. VA into RB parallel to the R5, R1 plus RB parallel to the R2, which is equal to VBE, which is less than of the 0.05 millivolt, and V is equal to 5 millivolt, which is given as the 5.54 millivolt. Okay, we should be okay before following this. We should be checking the thumb rule. That is thumb rule something that the air voltage gain is equal to 10 into 12, so 120. As per the ballpark estimation, what is the maximum rate of the voltage signal is something but without is equal just less than 5.5 millivolt, which is 151 times, which is equal to 0.8%. So finally, we have been solved all the problems and we have derived the current voltage gain, we derived the input resistance, and finally we have been deriving the by using the thumb rule, we have been find out the voltage here as 120 and the output voltage as 0.87 volt. So I'm going to see another problem combinator amplifier. So I want to say this is the last problem. So in this problem, we're going to see about combinator amplifier tools of the operation. Example. Problem. Find out the voltage gain, input, output, resistance for the circuit array. See, for the given circuit, I'm going to calculate the voltage gain and I'm going to calculate the input output resistance for this circuit above. Given beta f is equal to 65 and VA is equal to 50 volts. Assumption. Active region operation, VB is equal to 0.7 volts, small signal operating condition. Analysis. To find the Q point, the DC equivalent circuit is constructed. So from this, I got to construct the DC equivalent circuit, which is equal to 10 to the power 5 IB plus VBE plus beta F plus 1. IB is equal to 1.6 into 10 to the power 4 into 5. As IB is equal to 3.74 milliamps, and SI is equal to 65 IB is equal to milli microamps, and I is equal to 66 IB is equal to the group of 5 microamps. So therefore, 5 minus 2 to the power 4 IC VCE 1.6 into 10 to the ICE into its minus 4. Finally, this the thing has been equated to the 0. As VCE is equal to 3.67 volt. Yes, the thing has been continued over here. Common interactive rules of operation, for example. And in this slide, we could see we're going to get about all the things what we have covered in this time. We're going to talk about the GM, it's a transconductor and input resistance, output resistance, and final output resistance is the voltage gain and gain estimator. So how we here with these three circuits with the small signal analysis model, and then these circuits are going to get all the things. All in this depends upon the, but all in this the collectively it's a parallel resistance between RB and R5. So the value is 6.31 kilo ohms, and GM is equal to 40 IC, which is equal to 9.64 10 to the power minus 3 Siemens, plus R5 is equal to beta naught by 40 IC, which is equal to minus 6.74 kilo ohms. Whereas R naught is equal to VA plus VCE is equal to divided by IC, which is equal to 200 kilo ohms, right? And R out is equal to RC parallel to the R naught, which is equal to 9.57 kilo ohms. And whereas ABC is equal to AC divided by VI, we are divided by VI, obviously voltage is equal to output by the input. And this was characteristic of inheritance. All the depends upon the GM. It's a GM has conductance and the output resistance, which is parallel to the R drain, and the R entered by input resistance by the load resistance plus we can calculate these things without the analysis, without the voltage value, without the resistance value, we can, whereas resistances keep on varying, because these values we can calculate the thing. It's minus 84.0, whereas the minus sign indicates the signal the phase shift. Gain estimate is equal to A is equal to C is minus 10 volt, whereas VCC plus PE is equal to minus 100 volt. So, together comparatively, they affect the many things of this GM. So, many other things. So, using this small signal analysis, I can analyze the various parameters in the transistor. The transistor, I go to analysis, and I go to analysis the output resistance and output input resistance and the voltage gain factor and including the current gain factor. The purpose of this circuit analysis is to simplify it manner. Instead of dealing with the entire circuit, you can deal with only the AC operation. Since the DC voltage is fixed one, not going to change. So with sufficient number of setups, I could analyze all the things in this circuit part. So I think we are doing it at the end of this session. So here we're going to conclude this session. So thank you for attending my session. Well, in this we have been treated sufficiently all the things of the responsible model of BJT amplifier. So thank you for the session. Thank you.